Hi there students, welcome back to part 3 of Finance and Modeling. Here we're going to look at a more in-depth aspect of the logistic model and then the predator-prey or Lotka-Volterra model. This next example has been taken directly from the textbook, but it's quite typical in terms of what you can be asked in the matric exam. So there are some months, observed reliability, doesn't really matter too much about the context. And we would say, is this data a reasonable fit for a logistic equation? The way that we unpack whether something is a logistic model is if when we look at the change, the rate of change versus the population, if we get a linear decreasing function, that tells us that it is a logistic model. So if we want to check if it's a logistic model, we're going to have to play around and get this rate of change versus the population and some of the parameters around it. Then they say to us, create a logistic model and compare the results against the actual data values. So these are the data values here on my table. They're the observed values. Just one little thing to remember here, the change in population. What we do is if we're looking at a particular value at one point, we say look just beyond and look just before. And what we're going to do is we're going to find the average of those two values. Okay, so Pn plus 1 minus Pn minus 1, the one after it's the one before, and then divide by the distance, the period, the time between those two. So if we're just playing over here, we could create our table. So first things first, for example, if I'm looking here at this change in the population, what I should say to myself is, okay, by the way, go and index. That is quite important. Index the month starting off from 0 to 11. And then I'm going to say, well, if I wanted to find the change in the population, I would say, well, Pn plus 1 minus Pn minus 1. So it's the second minus that 0 month, which is going to be 12 divided by 2, which gives me a change in population of 6. So you can just see we go and create this column, which is the change in the population. And then what I do is I go and get the growth rate. Remember, this is, for all intents and purposes, the y value of our linear function. And you're dividing the change in population by the population. Remember, this is the population, which really is the x value. And so from here, I've got x values and I've got y values, but I've had to go and work out this growth rate, which is the change in population, which I first find divided by the actual population. Now I've got to go and create a logistic model from this, which is not so easy. And see what I've done here using computers on the next page. I have gone and I have plotted here the population versus time. Okay, so it's over, and you should be seeing I've got this wonderful smooth continuous S shape, which is telling me that I've got a logistic model. But that isn't sufficient. Okay, for us to show that something is a logistic model, we need to see that the growth rate against the population is a decreasing linear function. So if I just go back a page, okay, what I've got to do is I've got to find my linear function, and so I'm going to use core maths regression modeling. And I am going to go, so if you go into your calculator, that's at y hat is equal to a plus the bx. And these over here are all of my x values, and these over here are all of my y values. But please remember that when we were talking about the change in population, we were always saying, okay, the term before, the term afterwards. So clearly the first term doesn't have a term before, and the last term doesn't have a term afterwards, which is why these blocks are grayed out. They can't be part of the data. So I'd start off with x at 20, the y at 0,3, x at 26, the y at 0,307, and I would go and get this equation. Now I've just got the computer to draw this. You don't need to see this drawn, but I just wanted to illustrate that it is a decreasing linear function. But this is very important. This is what the regression line of best fit model tells me. And we've already seen from earlier on, this over here is the intrinsic growth. And if I just rearrange, and all that you ever do is it's your negative c over the m, or you're just finding the x-intercept, you get what we call the carrying capacity. So from this previous page, here from the regression model, I'm able to get your R, I'm able to get the carrying capacity, and hence I can go and create this recursive model. And if you just remember, your initial population, P0, is going to be the 14, because this is before we started, that was the initial starting value. Now I just want to pull up my calculator for a second to just show you something. So I'm going to type this in. So if our initial population is 14, I just type 14 is equals, and then I say to myself, that's going to change all the time. That's my population parameter. That's going to be the answer. So the answer plus 0.407 times by the answer, open your bracket, 1 minus, and then fraction, answer, and that's going to go over the carrying capacity, which is 101.75, close it off, and then press answer. This is the first predicted value using my model, and the second predicted value. And then if I just go down a page here, I just want to show you in the calculator. So these were the equation values. I'm here at 25.181. These were the observed data values in this green cell here. I am now finding these values. So if I press equals, you'll see 32.8934, press equals 41.95, press equals. And so this is how the recursive model using my calculator can generate the actual equation values, and then I could go and compare those. So let's just get out of here and go back. So quite often in the matric exam, you may be given a table like this, but there will just be a couple of unknowns. So for example, they would say, go and find this value, go and find that value, and then go and find the R and the K from your regression model. So you wouldn't find everything because it's just going to take too long, but you do need to be able to find these individual values, so just practice in your own time. And then we get to predator-prey models. Remember, this is a slightly simplistic model. So we model it on foxes and rabbits. Rabbits are obviously the prey. So it's highly unlikely that you're going to get rabbits and foxes, but it's easy enough for you to work out which are the rabbits in the context of the equation and which are the foxes, which are then the predators. Okay, it's simplistic. What we do is we say there are just rabbits living in a certain environment where there is a carrying capacity, and they're just eaten by the foxes. Similarly, nothing will eat the foxes. So the foxes will just eat rabbits and nothing else. And it's a very, very basic population model just involving those two animal types. Now we must just have a look again. Remember, any population model, okay, just always says, well, it's the previous population plus some change in the population. And so we're going to notice that this second part of our bracket here represents the change in the population, of which there's going to be some growth and there's going to be some decay, death, decrease in the population. So just be aware of that. And now we're going to look at some of the different variables and what they mean. So A is now the birth or reproductive rate. You should notice that it is no longer the R. R was the intrinsic growth rate. R was the birth minus the death. We don't minus the death anymore because the death rate is built into this decay here, because based on the foxes eating the rabbits, we're going to have some death rate over here and a decrease in the population. So you'll notice that the variable has changed from R to A, because it's no longer the intrinsic growth rate, but it actually is the birth or the reproductive growth rate. So this first part here is the growth. It's the increase in the rabbit population versus the decrease in the rabbit population. And so this total is the number of deaths. We refer to this as the attack rate. B is the attack rate on the prey. Then if we look at the foxes, foxes are also quite simplified. We've got this change in the population over here. There's a growth component, there's a death component, and we say that nothing else is eating the foxes. How nice to be a fox, they're just dying of old age. So this F now is an efficiency factor. It's a little bit more complex than just an efficiency factor, but basically based on the chance encounters between rabbits and foxes and deaths, this over here, this factor is going to increase the population. So that's reproductive growth. And the C over here is the natural death rate. Now you've got to remember that rabbits and foxes may actually have a different kind of life cycle. And so the examiner will generally standardize and tell you that we're working in a certain cycle. And so you've got to convert these different parameters. So the cycles may be in weeks or they may be in months. So read the question carefully. The bulk of the questions in the matric exams over the last couple of years have been in months, but look very carefully so that you can then modify the variable parameters into a certain cycle or period. Here is an interesting graph. If we're looking here at the prey versus the predators, okay, so the prey, so we've got some rabbits over here, and we've got some foxes underneath. This is a population versus time graph. That should be pretty standard. You should understand that when we notice that the distance between successive crests and troughs is diminishing, okay, so the amplitude is getting smaller, that tells me that our populations are tending towards some kind of equilibrium value. So we've got an equilibrium value here of just over 100. I don't know what that might mean. You know, if I've got nice scales, 110, 105 or so, and this equilibrium value there for the foxes is going to be about 50. But another interesting thing that we should notice is that the crests and the troughs are slightly out of phase, and it should make perfect sense. So what we should notice here is that if the rabbit population is starting to increase, because there are more rabbits, it means that there's more natural food for the foxes, which means then the efficiency with which they kill, and then the ability to make more offspring, that is going to increase the population. So it will always be slightly delayed. There's kind of a lag factor. And so now the fox population is starting to increase, which means they're starting to eat more rabbits. So then the rabbit population will take effect and start going down. And when there are fewer rabbits, that means then that we're going to have less food, and therefore the efficiency with which they're going to make little baby foxes is going to be less. And so these two graphs are always slightly out of phase. There's kind of a lag factor. But if they're tending towards a horizontal, or the amplitude is getting smaller, then we're reaching an equilibrium. This is a slightly different kind of graph, and this is known as a phase plot. So a phase plot will plot the two populations against each other. Okay, so we can see here our initial population, because that's where it starts, is 100 rabbits, and it looks like it's maybe about 8 foxes or so. And if we tend towards some inward spiral, if it is tending and converging to an inward spiral, we are reaching some kind of equilibrium value. It's quite important or quite useful to draw quadrants. In this particular example, the quadrants are not perfectly horizontal and vertical. What you should notice here is that I've got vertical, you know, the midpoint of all the x's and the midpoint of all the y's will give me my equilibrium value, but the intersection of these lines should also give me the equilibrium value. And then it's quite useful. So for example, if I'm looking in this particular region over here, which we might call quadrant 2, we could say in quadrant 2 we can see that both populations are decreasing. But if I looked, for example, in this quadrant 1, in quadrant 1 the prey is decreasing, but the predator is increasing. So we can see the predator is going up, and the prey is going down. So the different quadrants enable us to go and discuss what is happening to a specific population um, in one region, and also seeing if it converges to a particular point tells us if we get equilibrium or not. Obviously, if it's diverging, there's no equilibrium value, and this is known as a phase plot. Now, obviously, we might need to calculate the equilibrium points algebraically. So remember, the equilibrium point is when you get a steady state, and a steady state is when the change in the population is equal to 0. So what it means is the rabbit population at any one stage is exactly the same as the rabbit population prior, and similarly the same with the foxes. So I don't memorize these formulae. It literally takes me a couple of seconds to go and rearrange. But this over here stands for the change in the population, the second part. And you want the change in population to be 0, because then you're going to reach an equilibrium point. And so I say, if this is going to be equals to 0, okay, I'd make that equals to 0, and I could divide through by this rabbit part, and it's not too difficult to rearrange and to find the equilibrium point of the value of the foxes that would make this expression 0. And if I take the other formula, and we look at the fox formula and we say, okay, this is the change in population, and we want the change in population to be 0 for an equilibrium point, I can take out this fox part over here. And if I just go rearrange, again, is not too difficult to show. So this C, which is kind of this death rate, this kill efficiency factor, if I just create this ratio using these parameters, that will give me the equilibrium point for the rabbits. And then if I just substitute that into the other equation, which I had from earlier on, so there's two different ways in which you can rewrite this formula. So getting the fox equilibrium point, if I rearrange the formula with the parameters C, F, and B, or you can use the rabbit population from equilibrium point that you've already calculated and just substitute into that formula. But it's not too difficult to go and work out that equilibrium point. All right, let's now work through one last example. I hope you still got the energy, where we're going to create a model by finding each of the parameters. Okay, quite a long story. There's a lot to read, so we read very carefully. A certain species of rabbits. Okay, so if we're talking about the rabbits, remember we want to have some growth. The growth rate says how many offspring do we have, what percentage were female, and what was the percentage survival. So we're trying to find those parameters so that we can go and work out this. So we have 5 bunnies per litter on average, and 1 litter every 6 weeks. Okay, that's interesting. I just want to add something at the bottom here. We've been told that we're working on a monthly cycle. So what I would say here for the A, if we want to work on a month, I'm going to divide this by 6 and then multiply by 4. So I'm going to divide by 6 and times by 4 so that I can convert this to months and not weeks. And 4 6, so I'm then just going to be working out 2/3 of that total, which is 4 6. So I'd work out there are 5 bunnies per litter, 55% are female, and 70% survive to maturity. So I'm going to work that out on the next page just now. Let's just see. So there's the A, and I'm trying to find a K for the carrying capacity. Here we go. So it says a forest has, look here, initial rabbit population, initial fox population, and it can sustain 1,000 rabbits. So we've got our carrying capacity, which is cool. And then we've got to go and work out the B, the F, and the C. So they tell me that foxes live on average 42 months. So if we're trying to work out what the C is, then we'll say, well, what is the death rate per month? That would be 1/42th of that. Okay, so the C is going to be 1/42. I'm obviously choosing to do the easy parameters that we can find by inspection. So let's go and look over the page. It is very important that you know what are the initial number of rabbits and foxes. So let's go. Here are the formulas. Remember, you're trying to find an A, you're trying to find a K, and you're trying to find that B, which is the harder of those things. So the carrying capacity, easy, we've seen was 1,000. A, what we're saying to ourselves is, I'm just trying to remember what was the 55% of female, 70% of maturity. So this is the maturity, female, and then they're having 5 offspring every 6 weeks. I had to convert this. So this is just a conversion to months. Just remember, you've got to make sure that we're working in the same cycle. And then the C, well, they live 42 months, so 1/42th of it, there's my C. So I've already got a whole lot of the unknowns, and then I go and say I need to find the B. The way that I remember it is to say the B involves a decrease in the population of the rabbits, because in the rabbit formula, this is the decrease, and it leads to the death rate. So I just say to myself, find out in the first cycle how many deaths there are going to be. Okay, so in the first cycle, how many deaths? So I'm just going to go back and read carefully. So each fox will kill 4 rabbits per week. So then I say to myself, if I'm dealing with months, there are going to be 4 rabbits per week. That is how many are killed per month. But remember, each fox, and there are 30 foxes. So now when I multiply this over here, this is the number of deaths that I would get in the first cycle. The reason why we can only work in the first cycle is because the populations are going to start changing after the first cycle. So everything is always based on our initial values, which is quite important. So we go here and I say, this 30 times 4 times 4 tells me how many deaths there are in the first cycle. And then I use the initial populations. So there were 550 rabbits and 30 foxes, and this is the number of deaths, and then I just go and solve for the B. And that there is now the parameter for B, which tells me this particular unknown. I'm now going to use this unknown over here to help me go and find this F. So now the second part, and this is how I remember it, is to say, well, this is going to lead to an increase in the population of the foxes. So I say to myself, let's think about the initial increase that is going to take place. So the initial increase is going to be based on the initial parameters of the foxes and the rabbits. And then I say to myself, okay, there were 30 foxes, of which 15 were female. Now I just need to go back to the information. Let's just see. A female fox has 4 baby foxes in 1 year. So then I've got to say to myself, well, in 1 month, I must divide by 12. So it's going to have 15 are going to have 4 baby foxes in a year. So it's going to divide by 12. This is how many foxes it has per month. And there are 15 females. And so initially, this now tells me the initial growth. But you already have the initial rabbit population, you have the initial fox population, and you've calculated the B from above, so then I can go and find out what that F value is. So just remember, find B first leading to the F. Those are based on initial populations. The B is linking to the death of the rabbits, and this F is linking to the growth of the foxes based on the initial parameters. And then I've got my 2 formulae. And then finally, all that remains is for us to go and find the equilibrium or steady state values. And there, because I've got all of my values, I just go and use the formulae. So I've got the KACBF, remembering that the rabbit equilibrium value is C over F times B. It's very, very easy for you to just go and derive that formula. And so we find out that the rabbits are roughly 79. And in a similar way to go find the equilibrium value of the foxes, we substitute in your A's, B's, and you could have used this rabbit or the C over FB, and we work out that the fox equilibrium value is 41. Right, that takes us to the end of this module, but please, I encourage you, go through the Synstithians website, go and find past papers and practice, because the examiner is very creative and finds different ways to ask these questions, and you need to get exposure to all of these methods. Good luck with your final exams. Take care.